This is part 8 of the final exam review. This is on circular motion and gravity. We already made some videos on circular motion and gravity for the last test, and so if you had a hard time with the last test on circular motion and gravity, please go and consult the chapter 11 videos, because not the chapter 11, but the chapter 7 videos, because those really will help you understand the mistakes and so forth that you maybe made on the last test. We're talking about something called uniform circular motion. I have the word uniform underlined because uniform circular motion is a particular type of circular motion where you have an object moving in a circle at a constant tangential velocity, meaning that the tangential velocity as it's going around the circle is not changing. This is an object that's not speeding up or slowing down. It's going at a constant or uniform rate. So uniform circular motion means that your tangential velocity is constant. All right? Tangential velocity is constant. That's what the word uniform circular motion means. Now, anytime you have something traveling in a circle, let's say this is our circle here, there's an acceleration that's directed inward towards the center, and that acceleration we said was the tangential velocity squared over the radius of the circle. And if you have an acceleration, lo and behold, you always have a force. We called that force the centripetal force. That's why we put a little c there. Force, according to Newton's second law, was mass times acceleration. And if we're talking about centripetal force, we're talking about centripetal acceleration. And one of the problems on the test last time said to take Newton's second law and use substitution to come up with the centripetal force. So we just needed to take the expression for the acceleration and plug it in there to find that the centripetal force is mv squared over r. This is the tangential velocity. So this was our equation for centripetal force. That force is directed inward, so the inward force that acts on an object to keep it moving in a circle is the centripetal force, and that's centripetal, like a flower, like a rose petal. So that's one of the things that we discussed. Now, the other thing is that you always have to have this centripetal force, which is directed towards the center. You have to have that if you are moving in a circular path. So something has to provide this type of centripetal force. And we said if you're talking about a car or a bicycle or a motorcycle or any of these type of things, what's providing the centripetal force is the friction between the tires and the road. The force of friction is what's pulling the car inward to turn. So friction is what provides the centripetal force if you're a car, bike, or motorcycle, or anything with tires. If you have something on a string, suppose you're whirling a ball on a string in a circular pattern, then what's providing the centripetal force is the tension in the string. In other words, the string is providing that pulling motion inward. And if you're talking about an orbiting body, like the moon going around the Earth, then of course it's gravity that provides the centripetal force to keep it in orbit. Now, with that, let's just talk about gravity for a minute. The force of gravity, and this is Newton's universal law of gravity. So Newton's universal law of gravity is that the force of gravity is this capital G times the mass of one object times the mass of the second object over the distance between the two objects squared. You want to review this a little better, you could go to the videos on chapter 7. But this is Newton's Newton's universal law of gravity, where this capital G is the constant. That's the constant of gravity, or the gravitational constant. It is not the gravitational field. Remember, little g was the field strength. Little g was the field strength. Capital G is the gravitational constant. Anytime you have two masses, you have a force of gravity between them, and they attract and they're equal and directed towards each other. This little r squared is the distance from center to center between the two objects. So if you have two objects, and I put object 1 here, object 2 here, so this is object 1, this is object 2, this is mass 1, and this is mass 2. From center to center, let's say that's r, that's our distance. Now what happens to the force of gravity if you double the distance between these two objects? So now we're going to double the object's distance. This is object 1, this is object 2. We double the distance, so now we're twice r apart, center to center. And I want to know, how does the force of gravity now compare in this case? Suppose, for example, over here the force of gravity was 40 newtons in this case here. And we want to know what happens to the force of gravity in this case where the the distance between the two objects is doubled. Can we figure that out? Well, you need to know and look at this equation. This is Newton's universal gravitational equation. We need to look at that and see if we could figure out what's going on. So in the first case, this is the first case where we have force of gravity is 40 newtons. We have a distance r. In the second case, we have twice r. Well, let's see what happens to the force of gravity when we double the distance. So the force of gravity is equal to g mass 1 mass 2 over the distance between them squared. If we double the distance, then our new force of gravity is going to be g. Mass 1 and mass 2 aren't changing, but the distance now is changed. Now it's twice r squared. And when you do that, you come up with g m1 m2 over 4r squared. So you can clearly see then that the new g, or new force of gravity, is 1/4 of what you originally had up here. This is equal to 1/4 of what you originally had. So if that's the case, you double the distance, so you double r, you get 1/4 the force of gravity. So in this case, if our force of gravity at r distance was 40, you're going to have 1/4 of what you originally had. 1/4 of 40 is 10 newtons. So if you double the distance, you're going to reduce the force of gravity by 1/4, which means if you start with 40 newtons, you're going to have 1/4 of that, which is 10 newtons. So the force of gravity became less. Okay. Let's talk for a minute about a string, a ball on a string. Here's the tension in the string, and the ball is moving in a circular path. and all of a sudden the string breaks, and the ball, you know, is going to fly off in this direction because of inertia. So inertia is what keeps the ball in its tangential path should the force that's creating the centripetal force no longer exist. So in case you break the rope, the ball is going to go at its tangent velocity direction because inertia is going to keep it moving that way. And that's the type of things we talked about. Now, our accelerated class talked about Kepler's laws, and Kepler's laws very briefly. The first law says when we have objects in orbit, their orbits are elliptical. So we have elliptical orbits. Kepler's second law says, well, again, elliptical orbits with one of the objects at one of the two foci of the ellipse. So here's maybe this is the sun, and that's the Earth, and the Earth's traveling around the sun in an elliptical orbit. That's Kepler's first law. Kepler's second law says that if you have objects traveling in this elliptical fashion, then as the object's moving, and here's your central point that they're orbiting around, so the time it takes for an object to go from this position to this position, let's say, is t1. And when the object's over here, the time, let's say, it takes to go from here to here is t2. Then a funny thing happens if you look at the areas. Okay, area in this one, let's say, is area 1, and the area here is area 2. Kepler's second law says that in equal time intervals, so if t1 is equal to t2, then area 1 is equal to area 2. So in equal times, the planet will sweep out equal areas from the focal point, one of the two foci of the ellipse that it's orbiting. All of that goes to say that when you are closer to your body that you're orbiting around, you are going to have to move faster because you're going to sweep out the same amount of area. So when you're further away, you're going a little bit slower. So the further you are from the body, slower you're moving. As you get closer, the force is a little stronger, so you're going to have to go faster. You go faster, you're going to sweep out the same amount of area. The final law, Kepler's law, the final one, and again, this is just the honors class, was that the square of the period was proportional to the cube of the radius of orbit. And in fact, if we looked at that, we found that the square of the period equal to some constant times the radius cubed, and the constant we actually derived, and that's not, I'm not going to have you derive that kind of stuff. What you really want to know, it's sufficient for Kepler's third law for the purposes that we're working with, that the period, which is the time it takes to go around one revolution, the square of that is proportional to the cube of the radius. Okay, so that's it. We'll see you the next video.